Okay, good morning, everyone. Please, I hope you can hear me. Okay, nice. Please, do you have any comments or questions before we start today's section? Okay, I have one thing. So the last time I noticed after the class was over, right, and then I just checked the chat. I realized that at the very end, people were commenting about the 0/0, whether it was the same type. When is that type? Is that when we like there were questions on the chat which I didn't see. So usually, right, I'm interchanging between like about 3 windows: whiteboard, PowerPoint, and then what else? Yeah, and sometimes changing the color. So sometimes I don't see the charts pop up, right? So whenever I miss it, please feel free to draw my attention. Maybe unmute yourself, or someone can just alert me that there's something in the chat, like a question in the chat or something, right? Right. Okay. So that's my comment on that. So I think it's time. Is it? Yeah, it's 11 o'clock. So let's get on to work if there are no comments. Let me, wait, what's, oh, okay. People are waiting. Okay. So I think I've added everyone. Okay. So welcome back, right? So the last time, let me share my screen. Please, I'm sharing my screen. If you can't see it, do let me know. The last time we're looking at 2.3, right? So last time, right, last week, we looked at 2.3 and we were talking about a special kind of limit. That one, we know that when you're trying to find a limit, we try by first plugging in, right? But if you plug in and you get 0/0, that's a special type, right? That's why I said it's a type right here. So I made some notes. This was the first example. Example 3 was the first one, right? So I said for this type, the reason why we can cancel out some common factors is because when you are canceling out the factors, you're not looking at, so we looked at s squared minus 1 over s minus 1, right? So I explained that this could be 0. The expressions themselves are not equal. But if you're taking the limit as you approach it, then as you approach it, you're not really getting to the point, right? So you can cancel out without the factors being 0, right? If the factors are 0 up here and down there, like you see when s is 1, then you can't cancel this out, right? So that's why I said this is false. Maybe I'll be sticking with this instead of, so this one thing, this is the deal, right? When I do it this way, right? When I do it this way, I can only use like one color, right? But I think that one, you guys can see it better. But when I do it this way, I have more options, right? I can change stuff, colors and things up here. So I'll be interchanging between the two, right? Sometimes I'll zoom large if I think maybe the font size is too small or something, depending on the level of control I need, right? So that's just for you guys to know. So we wrap this up and then we started with some other examples. So looking at this, right? Looking at the second example, we said for this one, if you plug in, you're getting 0/0. So this is a type, right? It's type 0/0. So what do we do? Because it's just a rational function, it's a function over another, it's a polynomial of a polynomial. The simplification that we are going to try is, remember that for the type 0/0, the technique is try and simplify the expression and then you plug in the limit again, right? So the simplification that comes to mind when you have a rational function is what? Is to factor, right? So if you factor the numerator polynomial, the denominator is already in, it's a binomial, so it's as simple, it's as simplified as possible, right? But when you factor the top, you get s minus 5, s minus 1, and then all over s minus 5. Because you're taking the limit as you approach 5 and the expression doesn't necessarily get to 5, it doesn't, we are not looking at exactly 5, we can cancel out s minus 5 up here and s minus 5 down there, right? Because when it is 5, then it's 0, which case you can't cancel. But you are looking at the limit, and for the limit, we don't look at the 5, we're looking at the neighborhood of 5. So it is never 0. So we can cancel those out. And that reduces to this. Now we've simplified it. So what do we get? We plug in again, and that one gave us 4 without any undefined case, right? So that's the type 0/0. Please, any questions on this? So that was a recap, what we did last time. Okay, if there are no questions, then let's look at this. For this one, I have some space, so let me just do it here. So here, maybe let me use green, overwrite. So for this one, I'm trying to find the limit as t approaches 0. Let me split this. And then square root of t squared plus 9 minus 3 over t squared. Now, if I plug in, I'm getting 0 here, which is 0 squared plus 9, which will be 3 minus 3. That's 0. And then 0 squared down here is 0. You see, this type 0 over 0. So what do we know about limits that give us type 0 over 0? Well, that one, the technique we try is what? Try simplifying and then plug in again, right? And in simplifying, you usually cross out some common factors, right? So for this one, this is a radical. This is not like a rational function. You recall for the two previous problems that we saw, they were rational functions. So that one we factored. But the question is, if it's not a rational function and it involves radicals, what simplification comes to mind? Can anyone help us with that? What do you think? How can I get this to be simplified if it involves radicals? What would be what I should be thinking of? If it involves radicals, what simplification comes to mind? Anybody? Usually with radicals, if you want to simplify, what do you do? Yes, it's something related to that is used. Okay, something related, close. Anyone wants to try? Something involving radicals. What do you usually do when we want to simplify? It starts with R.
You rationalize it, right?
Perfect. You rationalize, right? The only simplification comes, perfect, Kenzie. So the only simplification that comes to mind when you're dealing with radicals is to rationalize. So in rationalizing, we multiply the numerator and the denominator by the conjugate of where the radical is. So in this case, because the radical is in the numerator, right? I'll multiply by the radical is t squared plus 9, square root of t squared plus 9 minus 3. So its conjugate is just change the middle sign, right? So that would be square root of t squared plus 9 and then plus 3, like so. And then all over what? I don't want to change the expression, so I also multiply the denominator by this, right? So I have t squared plus 9 plus 3. Please, are you okay? So that's the simplification you're going to do. And then when you get here, the numerator will always be, what you rationalize will always be a difference of squares. So you don't need to like stress too much with the simplification. All that you have to do is square the first term. So that'll be square root of t squared plus 9 all squared. And then minus what? Square the second term. So that'll be 3 squared. And then all over, we have t squared and then square root of t squared plus 9 and then plus 3. Right? So let's proceed with the simplification. So continuing with the simplification, we have the limit as t approaches 0. Now for this one, the square root and the square will cancel out. So I have t squared plus 9 and then minus 9 all over what? T squared. And then square root of t squared plus 9 plus 3. Please, are you okay so far? Any questions up to this point? Okay. Now moving on, the 9 minus 9 will cancel out. So I just have limit as t approaches 0 of t squared over t squared and then square root of t squared plus 9 plus 3 out here. And then at this point, because the t squared takes on 0 when it is at exactly 0, but then we are looking at the limit, so it never takes on actually 0. We can just cancel out these two. So we can cancel out t squared up here. No, that's 2. Yeah, so we can cancel out, let me find a different color. If this will do. We can cancel out these ones here, right? So that means you'll be left with what? The limit as t approaches 0 of 1 over and then square root of t squared plus 9 plus 3. Right. And then for type 0 over 0, what do we usually do? We simplify, and then after simplifying, we try plugging in again. Right. Please, anybody needs time here? I'm going to write the final answer on the next slide. Okay. Oh, need time. Okay. Okay. Fine. Okay, so that means we have limit as t approaches 0 of, what do we do? So we have this expression, so we plug in again, right? So that'd be, so let me just write it back here. So t squared plus 9 and then plus 3, right? So plugging in again, we get 1 over, so square root of 0 squared plus 9 and then plus 3. So that'll give us square root of 9, which is 3. So 1 over 3, that's 6. And you see this time, it didn't come out as an undefined case, and that's our answer. Please, are you okay with this? So that's how you deal with type 0 over 0. Any questions? Okay. Anybody needs time here? Could you simplify the radical first? Do you mean which part? The previous slide or this current slide? Before plugging in. Oh, okay. So at this stage, right, this is the best simplification we can do. You can't reduce square root of t squared plus 9. You can't simplify that. That one is in its simplest form. You see, it's not like, let me go back. It's not like, side note, right? It's not like square root of t plus 9 or squared. It's not like so. If it's like so, then it can reduce, right? I don't know if this is what you mean, right? But if you have square root of t squared plus 9, then it's still square root of t squared plus 9. Cancel it before plugging in. Which canceling? Do you mean cancel, like which one? There's radical with since the perfect squares. Oh, do you mean t squared and then 9? Oh yeah. So as I was saying, with the t squared and 9, if you have a sum of squares cannot be factored. A sum of squares is prime. You can't factor this. This just that. You can't factor this to cancel the square root. So square root of t squared plus 9 is still square root of t squared plus 9. You can't simplify that. You see? Makes sense. Nice. Okay. Then let's move on. Now, as you saw in the previous lesson, like 2.2, you saw that sometimes when we're trying to take the limit as you approach A, sometimes we got stuck. But then when we're stuck, we dwelt on the theorem that the limit as you approach A of f of x equal to L, if and only if the one-sided also agree on L. So sometimes if you are stuck taking the limit as you approach A, you can just take the one-sided, right? And if they agree on a value, then that'll be what? The same value as what? Your limit as x approaches A, right? So let's look at some cases where this comes to play. So an example is this one. So for this one, I'll show you two ways, right? So the first thing I try is, I'm trying to take the limit as x approaches 0 of an absolute value of x, right? We're already given the answer that is 0. So let's do this. So if you're given just this problem, how will you solve this? So I start by saying, okay, for this one, what is the technique I've taught you so far? I said, usually with limits, if it's easy to plug in, just plug in and see, right? So for this one, if I plug in, I get absolute value of 0, and that's 0. I'm done, right? But because this section is focusing on using one-sided to determine the general one, let me just use the one-sided. So how will you use the one-sided limits to figure this out? So let me say alternate solution. Right, so for the alternate solution, you can look at this absolute value of x. Now, absolute value of x is a piecewise function, right? The absolute value of x is going to be x if the x is positive, is 0 if the x is equal to 0, and it's negative x if the x is what? Is negative, right? Now, how am I getting this? How am I defining this? Remember the absolute value of 2 is 2. Absolute value of a positive number returns the same number inside here. That's why absolute value of x is the same x if the s is positive, right? And then absolute value of 0 is 0. That's why we are saying absolute value of x is equal to 0 if s is 0, right? Because if it's 0, it's just 0. And then the last thing is if you have, say, negative 3, absolute value of negative 3 is 3. Well, how am I getting this 3? This 3 is the same as what? Negating what is here, negative 3. That's why when the x is negative, the absolute value of x is what? The negative of the x, right? Please, are you okay? That's how I'm getting this definition. And this will come up later on in later sessions, so please note these. Please, any questions so far? Okay. So when you're taking the general limit, right, as you approach zero. So now let's look at this, the alternate solution. So you want to find the limit as s approaches zero, absolute value of x. So for this one, as I said, this is what you do in the usual case, but I'm using this to explain how we can use one-sided to still get this. So as you can see, this absolute value of x function is a piecewise function. So using one-sided limits, you can say, okay, now for the one-sided limits, let me try approaching zero from the right of this function. Let me just do this as it. So zero from the right? Now for zero from the right of absolute value of x, which piece of the function does this absolute value of x take, right? Well, it turns out that when you're looking at zero from the right, then you're looking at values to this side, and values to this side are always positive. The x is positive. You see, they are bigger than zero. So the values are positives. Now, what is the absolute value of x when it's positive? It's just x. So that means for this, I can just put in x here. And then when I get x, I can just plug it in again. So I get 0. So that's mine from the right. What about from the left? From the left of absolute value, oh no, I just wrote from the right again. From the left, what is the absolute value going to be? Now, from the left of 0, the absolute value of x is, like the limit is taken on numbers from the left of 0, right? So it's taken on negative numbers. And then from the left, the absolute value of x becomes what? Negative x. Right? So this one too, if you plug in 0, you get negative 0, which is 0. Now, because the two one-sideds agree, we can then conclude that the general one is also 0. Please, are you okay with this? So that's two ways of seeing this, right? But I usually go with a simpler route, right? This one. Please, any questions? Okay. Anybody needs time here? Okay, now let's look at this one. So this example says prove that it doesn't exist. So for this one, we have limit as s approaches 0 of absolute value of x over x. So what do? I first try plugging in. But then if I plug it in the top, right, absolute value of 0 is 0, and then the bottom is 0. So we are stuck, right? But when you are stuck trying to find the limit in general as you approach a number, what do? We try one-sided. So let me try 0 from the left and from the right. Now, from the previous section, I told you that the absolute value of x is going to be what? It's just x if x is positive, and it's 0 if x is 0, and it's negative x if x is what? Negative. So based on that, from the right of 0, right, you see that when you just have absolute value of x over x, you can't cancel out, you can't simplify. You can't simplify it out, right? But then, based on the definition of the absolute value of x, I can maybe do something with this, right? The absolute value of x will become x if I'm looking at 0 from the right, because for 0 from the right, x is taking on only positive numbers, right? So the absolute value of x becomes x over x. Now that I have x over x, I can cross them out, and I'll have limit as s approaches 0 from the right of 1. And what's the limit of a constant? It's just the constant. So from the right, I'm getting 1. Now let's do it from the left so that we can make a conclusion about the general limit, right? So 0 from the left of absolute value of s over x. This one too, you get 0 over 0. But then don't forget that the absolute value of s symbol, we can't cancel out, right? We can't simplify initially. But then note that when you're taking on 0 from the left, the x is taking on negative values. That means that the absolute value of s is what? It's negative s on that interval, on that set of numbers. Do you see? So that means that simplifies to what? Limit as s approaches 0 from the left. This negative x over x. And now with this one, we can cancel out the what? X over x. So that we get limit as s approaches 0 of what? Of 1, negative 1, sorry. So now what's the limit of a constant? It's just the constant. So we have negative 1. Now from the right is 1, positive 1, and from the left is negative 1. Therefore, we can conclude that as you approach 0, the limit what? Is dne. It does not exist. Please, are you okay with this? So that's how you show this. Any questions? And that's how you deal with absolute value limits. If they are type 0 by 0, right? Okay. Anybody needs time here? Okay, then let's move on. Now, what about this one? Now, we just saw that for piecewise functions, we just need the piece of the function, right? You usually find the limit by finding one-sided limits, right? And then we look at the piece of the function, given the limit, right? So for this one, we are asked to find the limit as s approaches 4. But for s approaches 4, because it's a piecewise function, we have to break it down into one-sided limits, right? Because the 4 breaks up here. The 4 is where the split is. So you have to use one-sided. So you go limit as s approaches 4 from the right. Let's try this one. Now, the thing with piecewise function is you just have to know the kind of piece that you're dealing with for the given limit. We know this function is square root of s minus 4 if the s is greater than 4. And it's 8 minus 2x if the s is less than 4. So depending on the interval that you're dealing with, the piece of the function changes, right? The function changes its form. So let's look at 4 from the right. All that we have to figure out is, for 4 from the right, which piece does the function take on, right? Is this the first one or the second one, right? So 4 from the right, notice that they are all numbers a little bit bigger than 4, right? So the x is taking on numbers a little bit bigger than 4. So which is it? Can anyone help us? Is it the first one? Or yeah, okay, I have the first. Do you have a different comment? The first. Okay, perfect. I have a second. Perfect, the top. That's correct. Thank you so much. That is correct, right? So when you are looking at 4 from the right, then it's taking on values here. That means that they're a little bit bigger than 4. And which piece of the function takes on values a little bit bigger than 4? Is square root of s minus 4. Is the top, this first one, right? So that means that for this limit, we can just write it as what? Limit as s approaches 4 from the right of f of s. It's just the limit as s approaches 4 from the right of what? Square root of x minus 4. Now that we have the actual function form, we can kind of what? Try and plug in, use the technique that we've learned, right? So just plug in. So what do you get? You get square root of what? 4 minus 4, right? You plug in the 4. So that gives us what? Square root of 0, which is 0, right? So that means from the right, limit as s approaches 4 from the right of f of x is equal to 0. Now, what about from the left? So from the left too, let's figure out the piece of the function. So from the left, what do we have? We have limit as s approaches 4 from the left. But which piece does it take on? Now note that from the left, it takes on what? Smaller values than 4, right? Its values a little bit smaller than 4 because you're looking at something like 3.99999. And which piece of the function is there? It's just the second one. I just said it because it's just two options here. If the from the right is the top, then from the left is here, right? So it's just this one. It's 8 minus 2x because that's for when x is what? It's less than 4. So that means this one is just going to be 8 minus 2x. Now that we have the function form, we can just plug in. So we get 8 minus what? 2 times 4, which is what? It's also 0, right? Now, because from the left and from the right are both 0, we can conclude that in general, the limit as s approaches 4, right, of the function is equal to 0. Please, are you okay with this? So that's how you deal with piecewise functions. Any questions? And then also the fact that you have to also note that when you're dealing with general limit, sometimes you may have to use the one-sided limit to confirm your results. And that's all on that. Any questions here? Anybody needs time? Okay. Now we are going to conclude, right, with a kind of theorem, like some theorems here. So for the first theorem, if a function f of x is always less than or equal to g of x, when s is near a, right, then the limit as you approach a of this function of f of x will also be less than or equal to the limit as it approaches a of g of x. So this kind of like you are relating these two. Sometimes you may have information about this, or it may be easier to take this limit than that. And in that case, you can at least have a boundary information about what the limit, the upper bound of what the limit of f of s as s approaches a will be, right? So that's when this can become useful. Now, a very important theorem also, which is very, very useful, is this one, the squeeze theorem. Some call it the pinching theorem. Some also call it the sandwich theorem, right? The sandwich theorem. So what is this saying? The squeeze theorem says, if you have a function g of x, squeeze in between two functions. So that means you have kind of like a lower bound, right? F of x less than or equal to g of x less than or equal to h of x, and then an upper bound h of x. If g of x is squeezed in between these two, that's why it's a sandwich. Do you see? It's kind of like this, like the inside, and then these are the bread pieces. Yeah. But then what this is saying is, if you have this, when the x is near a, well, except possibly at a, and then you are able to figure out these two limits, the limit of f of s and then the limit of h of s, are both approach a, and then you notice that they are both L, then the middle function will also be L. So that's the power of the squeeze theorem, right? So if you have a function sandwich in between, and then you realize that the limit of the ends of the bounds, right, the boundary functions are also L, then the middle will also be L. Please, are you okay? So that's the squeeze theorem. I'm going to, I think we'll show it on a graph, and then we do a question. You'll see the power of this theorem on the last slide. Please, any questions here? Anybody needs time? Okay. So this is a graph showing the squeeze theorem at work, right? So you can see that for this one, you have g of x here, sandwiched in between the two, h of s and f of x. And you're looking at the limit as you approach a. And as you can see, because it's less or equal to, the g of s is in between the two near a, then their limit is also what? Is the same. Right, so that's this is just illustrating the curves. Please, any questions here? Okay, so let me, oh, you need time on this. Okay, wait, is this one or the previous slide? This one. Last, the previous one, this one. This one. Oh, am I showing the wrong slide? Do let me know if I am. Okay. I think you guys, you have the right slide, so. You're good. Okay, were there two people? Sometimes it's easy to miss a chance when last slide. Oh, is everyone good on this one? Everyone's good on this, right? Okay. Yeah, perfect. Okay, then let's go to the last question. So when do we apply the squeeze theorem, or what's the relevance of this? So for this one, we have this. So we have limit. Let me change colors. So you have limit as s approaches 0 of s squared sine of what? 1 over x. Okay, so we are already giving the answer. We are giving it to be 0. But suppose you're giving this. How do you solve this? Okay, so for this one, I try the limit of a product of functions. This one involves s squared and sine of 1 over x. So let me try and analyze and see what these limits are. So for the first one, let's say 0 squared, that's 0, right? And then for the last one, I have sine of like a kind of like a 1 over 0. This is a non-zero number over 0, right? This is a non-zero number over 0. So for this one, I know my answer is, this is general. So I know my answer is either going to be positive infinity, negative infinity, or dn. But then the question is, let's just focus from even one side. Let's suppose we are looking at 0 from the right. Suppose we are looking at this. Then we just have 0 times, so sine of 0 from the right to be something like 0.00000001. So what would this be? What is sine of 1 over 0.0001? This one would be like 0 times sine of something like an infinity. But then let's pay attention to the sine function. You notice that the sine function oscillates. Sine of 0 is 0, sine of pi on 2 is something like so. So this is sine of x. Now, the sine function oscillates as you approach infinity. It oscillates between -1 and 1. You see, it oscillates between -1 and 1. That means it's not taking on a specific number. So that means that that limit is DNE, right? And if you look at it from the left too, you get a sign of something like a sign of something like a negative infinity, right? I mean, that's not a valid thing to say, but I'm just analyzing, right? So as you approach negative infinity 2, it's also oscillating between -1 and 1. You see? So that means that that limit also does not exist. So in either case, we are getting like this thing is giving us something like a 0 times DNE. It's giving us something like 0 times DNE. And you can't multiply a number and then something that does not exist. So that means you are stuck. For this, you are stuck. Without the squeeze theorem, you can't do anything with this, right? But then you notice that sign of anything is actually squeezed in between two functions. The sign of anything is always in between what? 1 and -1. Sign of something is always in between 1 and -1. Now, because we have these boundary conditions, we've been able to squeeze this function inside this. Now, the expression we are dealing with is s squared times the sign of something. So, and s squared is positive. So when you multiply by each of the terms, right, this three-part inequality by each of the terms, you multiply each of the terms by s squared, you don't change the inequality. So that means I can multiply the -1 by s squared. I can multiply the sign of 1 over s by s squared. And then I can multiply the 1 also by s squared. So what have I obtained? I now have this function squeezed in between 2. So I have s squared sine of 1 over x. And then into s squared. So now that I have the expression in between two functions, let me try and use the squeeze theorem, right? So let me try and use the idea of squeeze theorem to obtain this. So I try limit as s approaches 0 for the negative s squared. What do I get for this? I just plug it in. So I'll get -0 squared, which is 0. What about the limit as s approaches 0 of what? Of s squared. That's also 0 squared, which is 0. Right? That's 0. Do you see? The two are 0. So for the lower bound function is given as 0. The upper bound function is also given as 0. So by the squeeze theorem, let me perhaps create a new one. Control M. Oh, by the way, anybody needs time here? Okay. The chat keeps, okay, yeah, I think it's stable now. Okay, wait, you're good. Jacob, are you good? Okay, so as I was saying, by the squeeze theorem, because the limit of the upper bound function and the lower bound function are giving us 0, we have the limit as s approaches 0 of s squared and sine of 1 over x is now 0. Now, this is one of the reasons why I don't want you to say that 0 times DNE is DNE, because if you had done that, then in this case you'll be wrong. Do you see? That's why we don't do operations on a number and then DNE. We don't do 0 plus DNE. You can't say that one is 0, right? Because 0 times DNE, you can't say it's DNE. Could be 0 for all you know. Yeah. Please, any questions on this? So that's end 2.3. That was a long one, but we are learning a lot of techniques, right? A lot of limit techniques. Would the -1 change if the amplitude, or is that something you will need to trip? Yeah, you don't have to worry about that because this one is just automatically in between these two, right? -1 and 1, for whatever sign it is, right? So as long as you get it to be sandwiched in between two functions, and then the limits are the same, then you conclude that the middle is the same. Sometimes you may not even have information about the function in between the two. You just have information about the upper function and the lower function. But employing the squeeze theorem, just take the limit of the bottom and the limit of the top. If they are the same, then the limit of the middle is the same. That's the squeeze theorem. Please, any questions here? So that's 2.3. Okay, then let me move on. Save. Save. I think I opened 2.5. Okay, so I'm sharing 2.5. Please, if you can't see, do let me know. So for 2.5, we are looking at continuity, right? Continuity. So you notice that when we are trying limits, what do we usually do? Well, we try and first plug in, right? We plug in. You can't see. Oh yeah, 2.4 is, you're not responsible for 2.4. That one deals with like a precise definition of a limit. Yeah, 2.4, you're not responsible. It's not part of the syllabus. Okay, so you notice that for some of the limits, we just plug it in the expression and then we get the same thing, right? If it comes out the same, then that's your answer, right? Say you're taking the limit as your pre-sum number and then you plug it in and you don't get undefined, then that's your answer, right? So this is a characteristic of continuous functions, right? So the limit of a function as s approaches a can often be defined simply by calculating the value of the function at a, right? If this can be found or this can be obtained, then we say that the function is what, continuous at the a, right? Now you see continuous in the daily language, right? Continuous means it's flowing, it doesn't stop, right? It continues. It's funny how I'm using the continuous to explain continuity. Wait, so continuous means it just follows without stopping. I think that works. Yeah, it just follows without stopping, right? So it flows. But in the mathematical language, right, when you say something is continuous at a number a function is continuous at a number a, then we just mean that the limit as s approaches a of the function is the same as what? Plugging in the a into the function. So it's the same as what? F of a, right? So if you have this condition to hold, then we say the function is continuous at a. And that's the definition of continuous at a. Please, any questions here? Okay. Now, this definition you see here means three things, right? If you are saying the limit as s approaches a of f of x equal to f of a, then that means three things have to hold for this equality to hold. So what are the three things? The first thing is the function first has to be defined at a. If the function is not defined at a, then it can be continuous at a, right? So f of a is defined. That's the first one. Now, the second point is the limit as s approaches a of the function has to exist. If the limit does not exist, there's no way you're going to have a to equal to f of a, right? So that's the second point. And then the last point is the same as the original definition, right? So if the a of a is defined and then the limit exists, they have to be equal. So for a function to be continuous at a point a, these three have to hold, right? In other words, this single definition is in three parts, which are these. So you have to check for these and make sure that they hold for us to conclude that the function is continuous there at a point a. Please, are you okay with this? Any questions on this? Anybody needs time? Oh, okay. Okay. So one thing I always say is don't forget that all the stuff are posted. You don't have to write too many stuff, right? I post all the slides. I post everything that I write on there. So, and then with a limited time to try and make your notes as brief as possible. All of these will be available on the file section of Canvas. But still, let me wait. You still have to make notes though if you want to. Good, okay. Okay, so if a function is not continuous at a, right? In other words, if any of the three things that we talked about here is not true, then we say that the function is discontinuous at a. So it's either continuous at a or it's discontinuous. So if it's not continuous, then we say it's discontinuous, right? Now, a lot of physical phenomena are continuous, right? For something like displacement or velocity of a vehicle, it varies continuously over time. Your height is a continuous function, right? And then discontinuities occur in like electric current. So these are places where you see these at play, right? So they are just examples. Now, this is the one fun part, right? When you're dealing with a continuous function, all that you have to think of it is geometrically, right? A continuous function at every number in the interval is a function whose graph has no break. So let me give you examples. So a function like this is continuous at every point. A function like this is continuous. Why? Because when I'm graphing this, I don't lift my whatever my pointer that I'm using. In other words, I can just graph it without lifting it off what I'm graphing it on, right? So whether it's pen to paper or pencil to paper or whatever, you can just grab the function without lifting it off the paper. Do you see? Yeah, so that's a continuous function. Now let me show you some cases of discontinuity. So the function is discontinuous at this age. So let me say I'm graphing something like this. And then when I get here, I have to lift it off before I get here. You see, there's a lifting of the paper and then continue here. So it's discontinuous here. The difference between this. Oh yeah, no, I'm not doing a sine function graph. I'm just illustrating that it just flows without me lifting my whatever. So let's whatever. I don't want to talk about stylus on this. If it were we were in class, I would just say without lifting my marker from the board, right? But what I'm saying is with continuous function, I'm not looking at the sine function only. The sine function and the cosine function are perfect examples of continuous functions. They are continuous everywhere because when you are graphing them, you don't lift your pencil or your pen from your paper. You can graph it flow, like you can just flow without lifting it off, right? For this discontinuous function, when I get to this point, I have to lift it off. When I grab this, I have to lift it off and then get here and then shade before I can continue. So I know that there's a break. So that's how you figure out whether there is a discontinuity or at a point or not, right? It's going to be continuous if you don't have to lift your pen from your paper when you're graphing it. So these two are just examples. So this one is continuous everywhere because I can just graph it it will just flow without me lifting it off, right? But for this one, it will be discontinuous here. Please, does that make sense? Are you okay? Perfect. Okay, so these are just examples. So now with the example set, let's look at this exercise, right? Let's try and work out how we're going to figure out whether a function is continuous or not. For this one, I think perhaps we should, okay, the answers are, some of the answers, at least one of them is here. Fine, it's fair enough. Let's look at this. So for this one, it says fig 2 shows the graph of a function f at which numbers is at which numbers is f discontinuous and why? At which numbers is f discontinuous and why? So for this one, let's look at this. Let's look at from the left to the right. The first point is already here, so let me just talk about that one. At least that will serve as a solution, my first attempt with the class. So if I move from the left to the right, you see, if I grab this graph, when I get here, right, when I get there, I'll have to do something like this. Take my pen from here and stick my stylus and then continue. So I know that for this one, the function is what? Is discontinuous here. The function doesn't flow. Well, someone might say, well, technically I can just pass over it twice and then get back and continue. Well, the thing is, you don't pass through the same line, right? Don't pass through the same line twice. So if you're getting here, try and see if you can find a way to grab this without passing it through the same line and then continue. You can't do it, right? So you have to lift it off and then continue from here, right? So that's what I mean. So here is discontinuous at this point, right? So it's discontinuous at 1. But that one is like a geometrical way of seeing this. Looking at the definition, the 3 conditions that we gave, which one does it violate, right? Which one does it violate? Well, you can see that because there's a point show here, f of 1 is not defined. F of 1 is not defined. So that's the condition. So it violates the first condition. This one, I'm talking about this one. F of a is not defined, right? So f of 1 is not defined. That's why it's discontinuous. So that's how we say it mathematically. F of 1 is not defined. So the function is what? Discontinuous at 1, right? So there's discontinuous at 1. Okay, so I did the first one. So can anyone please help us with, from the left to the right, can you see any points where the function is discontinuous? Do you see any points where the function is discontinuous? What do you say? Can anyone please? So I have 3. Thank you, Megan. Anybody else? You agree with 3?
5.
5. Perfect. Thank you, Mallory. Okay, so I have 3 and 5. Perfect. Okay, so let's look at the 3. So at the 3, you notice that geometrically, if I'm graphing this, when I get to the 3, I'll shade this point and then move my stylus from my surface, and then get to this point before I'll take this second and then continue with the graph. So I know that the function is discontinuous at 3. So that is true, right? But looking at the mathematical definition, which condition does it violate? Which one is it? The question is f of 3 defined? What do you say? Is f of 3 defined? Is it a yes or no? What do you think? So I have no. Is f of 3 defined? A seconder to this or a different answer? Come on, just speak your mind. I mean, if you are wrong, no one's gonna. Okay, I have no. Well, in this case, the answer is what you propose is incorrect. F of 3 is defined. F of 3 is this point. You read f of 3 from here, the shaded point. F of 3 is this point. So it's not the first condition. As I say, feel free to make your mistakes here. It's fine, you make it here and then get it right on the exam or on a quiz. So f of 3 is defined. So that's not the condition. Now the next thing is, does the limit exist? Does the limit exist? Does the limit exist? That's the second thing you have to check. So does this one exist? Limit as s approaches 3 of f of s. Does it exist? So I have no. Perfect. The limit does not exist because if you approach it from the right, you are getting it to be a point up here. If you approach it from the left, you are getting it from a point down here. So the limit does not exist. Right. So that means it violates the second condition. The f of 3 is defined, but the limit does not exist. So that's the reason why it's discontinuous at 3. The limit does not exist. Please, are you okay? I hope this makes sense. Okay. Now, someone also said when s equal to 5. Now, don't worry about what I'm doing because the slides will explain everything, right? It's going to explain everything down here. So we are just explaining to understand this without looking at the answers. But the answers are all explained in detail down there. So don't worry about how I'm writing these scrappy things here. Okay, so now let's look at 5. Let's do this together. The question is f of 5 defined? Is f of 5 defined? So I have no and a no. I have none.
Yeah.
Okay. Yeah. Okay, I have yes. Like, nice. I like different. Yeah. Okay, so for those who said yes, your answer is not incorrect. So you are right. So f of 5 is defined. As I said, when you're reading the exact value of the function, be careful with points to shaded points. So f of 5 is this point. This is f of 5. It's defined. So when you're reading f of 5, you read it up here. So it's defined. So it's not violating the first condition. Now let's check for the limit. What's the limit as s approaches 5 of the function? Does it exist? So I have a no.
Yes.
So I have a yes. A seconder to either one, I have a yes. Perfect. The limit as you approach 5, it exists. So from the one, because you're looking at the general one, you have to look at from the right and from the left. From the left, it's approaching this point. From the right too, it's approaching this point. So the two-sided agree on that point. So the limit exists. Okay, so the second one also, it passed the second test. But what about the last one? The limit as you approach 5 of the function, is it equal to the function at 5? Well, for this one, you can see that the function value at 5 is up there. And then the limit will be somewhere down here. Is this point 2? Do you see? The limit will be something down here. Is this point down here? So that means the two are not equal. Right? The two are not equal. They are not equal. So that means that's the condition is violating. Right? The function is defined, the limit exists, but the two are not equal. So that's what's happening at 5. So we can say the function is also what? Discontinuous at 5. Please, are you okay with this? Any questions? I hope it makes sense. Okay, so as I said, don't worry about writing all of these. The explanations have been given here, right? That's why I just wrote everything out here. Please, are you okay? Any questions here? So that's how you do it. Okay. Now, the one that we saw was a graph, but what if we have something like a function, right? Something expressed in function notation, right? An explicit formula. How do you figure out where it's discontinuous and where it's not, right? I think because of time, we have to stop here. 12:50. Or do you want me to go on till 12:50? That'll be fun. I'm just kidding. Okay, yeah. So I think that's all. No. I think your 12:50 idea sounds fun. This would have been nice if I can sneak out some hours. But still, thank you for your time. So see you on Wednesday. All the best. If you encounter any issues, feel free to send me an email. If you want to schedule office hours to do, let me know. All right. So that's all for today. We'll continue with example 2 on Wednesday. Thank you for your time. All the best.
Thank you.
You're welcome.
Thank you, Professor.
You're
Thank you, Professor.
You're welcome, Hunter. Welcome, guys. All the best.
Thank you.
You are
Thanks,
welcome. Yeah, you're welcome. Let me save this.
Thank you.
You're welcome, Shane.